Let's start lecture of graph algorithms. A set of vertices, the set E is the set of pages. Graph models is used for modeling the relation between objects. In any application that we have some objects, some entities, and there are some relations between these entities, we can model this relation by a graph. Okay.
Yes.
We can show entities or vertices or node of graphs by, for example, zeros. We have some vertices, some nodes, and there are some relation between these nodes or these vertices, and the relations are shown by lines, by some lines that are connecting vertices. For example, we may, this is an example of a graph. In this graph, we have 5 vertices. We can give numbers to vertices, for example, 1, 2, 3, 4, and 5. So set of vertices is a set of 5 objects or 5 numbers. 1, 2, 3, 4, and 5. And the set of pages is a set of pairs, set of ordered pairs. For representing age that is connecting node 1 to node 2, we use pairs which consists of 1 and 2. The pair 1 and 2 is related to the edge that is connecting vertices 1 and vertices 1 and 2. So we have these edges 1, 2, 2, 3, 1, 3, 3, 4, 4, 5, and 5, 1. We have 6 edges in this graph. So graph is a mathematical structure consisting of 2 sets, set of vertices and set of edges. The set of vertices correspond to a set of objects or a set of entities. And there is a set of ages. The set of age shows the relations between objects, the relations between entities, relations between vertices. Okay, we show a set of vertices or set of objects by V and set of edges by E. Okay, this is the concept of graph. Okay, no, graph may be directed or undirected, may be connected or unconnected, may be weighted or unweighted. We talk about this. An edge between a vertices I and vertices J may have not any direction. Okay, there is no direction for this edge. In this case, we say the graph is undirected. Undirected graph. In undirected graph, the edges do not have any direction. Undirected edges are used for modeling the relation. For them, there is not any direction. For example, friendship has a relation that does not have direction. For example, Ali is friend of Reza, and Reza is friend of Ali. The friendship is a direction that do not have is a relation that does not have direction. But some relation may have direction. For example, Ali is employee of Reza. Okay, this relation, the relation of employment, the employment relation is a directional relation. In this relation, we use directed edges. I is connected to J. There is a directed edge from I to J. Okay, from I to J.
Also, excuse me, sir. Also, son and father.
Yes, son and father is a directed concept. So we should use directed edges and directed graphs. Okay. For example, for undirected graphs.
Sorry, Doctor. Which topic for what? This topic for what? Now, pairs first search and depth first search. We arrive.
We are talking about this. Okay, please let's define graphs first. Then we are going to talk about DFS and BFS. Okay.
Okay, and this new subject now?
Yes. In the following, I talk about BFS and BFS. Okay.
Okay, that's it.
Like son and father. Okay. So we have directed graph or undirected graph. Okay. Also, we have weighted or unweighted. An age may be assigned number to it. For example, age I, the age between I and J can be assigned a number to it. Can be assigned a number. For example, 5. This is the weight of the age. Okay, so if the ages have weights, have
one row.
Okay.
Depend on 3 circle above. You put 1 on 3 column and 1 row, and you put 1 in 3 column second row. Depends on this 3 circle above. So from where you put 1 and 1 in the third row. How you put? Depend on what?
Because this graph is undirected, okay, we have an edge from 1 to 3 also in matrix. We go to row number I and column number J and see if here is 1 or 0. We check A, I, J in constant time. Okay. But in adjacency list, we should go to linked list I and traverse the linked list to find if there is J here or not. Okay. This needs at most OV time. But here O1 time, a constant time. Okay. So matrix is faster than list, than adjacency list. Okay. Any question? I think there is a question about the storage, okay? The size of storage. Size of storage, I explain again. Adjacency matrix have V rows and V columns. The number of rooms is V multiplied by V, which is V power of 2, okay? For adjacency list, we have a one-dimensional array which has V rooms. So we have size V plus for every record we have a room for any record, and we have a record for each edge. So the number of records is equal to the number of edges. So the size of adjacency lists is V plus E. But the number of edges, or E, differs in graphs. We may have no edges, so the number of edges may be 0. Okay, but in complete graphs we have V multiplied by V minus 1 edges, because each vertex has an edge to any other vertex. So the number of edges varies between 0 and V multiplied by V minus 1. So the term V plus E is between V and V plus V multiplied by V minus 1. Okay, so it depends on the number of edges, how many edges we have in graph. We may have low edges, we may have few edges, we may have many edges. Okay. I have a question from you. If you passed the data structures course or algorithm design course in your previous degrees, in bachelor or in master degree that you have passed, do you have data structure course, or do you do you have algorithm design course?
Yes, doctor. We
Okay.
have both authorized here.
Okay, but I think there is a big gap between that time and now. Okay, or not?
Yes, exactly.
Okay, so you may forget that concepts. Okay, you may forget that concept. So because of that, we are going to reteach that concepts, and because of that, I think there are many questions, because you have taught these concepts a long time before.
Yes, exactly. More than maybe 10 years.
Okay.
Doctor, excuse me. Last time you said you will send accessories through the system, right?
Yes, yes. We are. I think it has put on the system, but if it is not currently on the system, I asked my TA to put it, and also I send. You can email. Also, you can email me to give the exercise and share it with the others. Okay.
Okay, I'll send you email.
Okay. Thank you. Okay. One of the students asked me, please repeat the last explanation. You know that the number of edges in a graph may be 0. Okay, we may have only some vertex with no edges. For example, we have four vertices with no edges. Okay, the number of edges here is 0. Okay, but we may have all the edges. In the worst case, we have all the edges. So in this case, the number of edges is v multiplied by v. Okay. If we consider all the directed edges. In this graph, any vertex has an edge to any other vertices, to any other vertex. So any vertex has v minus 1 edges, and we have v vertices. So the number of edges is v multiplied by v minus 1. So the number of edges is not fixed. It depends of the number of edges. It may be 0 when there is no edge. It may be v multiplied by v minus 1 in the worst case. So v plus e is v in the best case, in the at least it is at least v, and at most v plus v multiplied by v minus 1. Okay.
Doctor, please. The last statement.
Okay.
In the middle, v plus h.
V plus e.
Yes. Can you explain it why we put it here? V plus.
in adjacency lists, we have a one-dimensional array. Okay, this one-dimensional array. In this one-dimensional array, there are v rooms. Okay, 1, 2, 2 v. Okay, so we have v rooms for this one-dimensional array. Also, we have a record in the linked lists. A record in the linked lists for each edge. Each edge have a record. Okay, so the number of these records in the linked lists is equal to the number of edges. Okay, so the total number of rooms is the rooms that we have in this one-dimensional array, and the rooms that we use for records. Okay, for records, I mean these items. Any item of a linked list maintains ID of an age. Okay, for example, age for age I j, we have a record here. We have an item here that contains j inside it, and this item, this record, represent age ij. So for each age, we have a record in linked lists. So the number of records or the number of rooms that we used for storing ages is equal to the number of ages. So we have v plus e room. We need v plus e rooms because we need v rooms for this one-dimensional array, and we need e rooms, the number of ages. We need the number of ages rooms for each of this record that store an age. Okay, is it okay? Okay. So let's talk about algorithms. DFS and BFS algorithms. DFS is stands for depth first search, in brief DFS, and we have brief first search, in brief it is BFS. What are these algorithms? These algorithms are exploration algorithms. What does it mean? It means that in a graph we can start from a vertex and go to other vertices by edges of the graph. For example, we can start from vertex number 1, then by the edges that are in the graph we can go through edges and reach to other vertices. So we can go from vertex number 1 through edge 1, 2, through edge 1, 2, and reach to vertex 2. Then we can go from vertex 2 to vertex 3 through the edge 2, 3. And we can move in the graph. We can move through the edges and go from one vertex to another vertex. We walk to inside the graph. Okay. We are going to see any vertex. Okay. We explore. Suppose each vertex is a city, and between two cities there is a road. There is a road. If there is an edge between two vertices, this means that there is a road between corresponding cities. If we are in city number 1, okay. Suppose this is a map of cities and roads and roads. Roads between cities. Road can be considered as edge, and city can be considered as vertex. We are in one city and want to go to the other cities through the roads, so we walk through roads and reach to next city, and then we continue and walk through the other road and go to the other city, and we are going to visiting all the cities. Okay, this is the exploration. Okay, by exploration we mean visiting any vertex, any vertices of the graph. We have at first we at first are in one city, in one vertex, and we are going to walk through edges and see every vertex. Okay, this is the exploration. So in exploration we are going to explore, we are going to visit every vertices of the graph. Okay, exploration is equal to visiting all the vertices of the graph by starting from one vertex. We are at first at a starting vertex. We are at a vertex at first, then we go through edges and visit the other vertices. This is exploration. There are two famous algorithms for exploration. Okay, we are going to talk about these algorithms. Let me first talk about depth first search algorithm, or DFS. I'm going to explain the algorithm on an example. Vertex 2, vertex 1, vertex 3, 4, 5, 6, 7. Okay, suppose at first we are in vertex 3. At first we are in vertex 3. This is a start vertex. Okay, we are going to visiting all the vertices by walking through edges. We are at vertex 3. What we do in DFS? In DFS, we go from the current vertex edition of the book. In the second edition, chapter 22. Okay, chapter 22, elementary graph algorithms. So I write the chapter title. Chapter of the book. The title of the chapter is elementary graph algorithms. Okay. It's 22 in second edition, but in fourth edition I do not know what's the chapter number, but the chapter element is elementary graph algorithms, where we talk about BFS, DFS. Okay. Okay, let we go for BFS and DFS algorithms. Now we have a brief familiar with graphs, and we know how graphs are stored in the memory of computer. They can store in adjacency matrix, or they can store in adjacency list. Adjacency matrix is a V multiplied by V, or has V multiplied by V rooms. I mean V power of 2 rooms. But adjacency lists has V rooms for a one-dimensional array, and the number of records of the linked list is equal to the number of edges. So we can compare the storage of these two data structures. The storage of matrix, adjacency matrix is V power of 2. So let's talk about the number of edges in a graph. A graph, if in a graph there is all the possible edges, if we have V, excuse me, V1, V2, V3 to Vn. Suppose the number of vertices is n. If we have n number, if we have n number of vertices. Number of vertices is equal to n. So the number of possible edges maybe at most n multiplied by n minus 1 because each vertex may have an edge to each other vertex. So each vertex may have n minus 1 edges, and the number of vertices is n. So the number of total edges may be as large as n multiplied by n minus 1. Okay. And also we may have no edges in graph, so the minimum number of edges is 0. So we have the number of edges is between 0 and n multiplied by n minus 1. The maximum number of edges is n multiplied by n minus 1, and the minimum number of edges is 0. Okay. So if you have all the possible edges, we say the graph is complete. Complete graph. Complete graph is a graph that has all the possible edges. So has n multiplied by n minus 1 edges, a complete graph. Okay. So depending on how many edges we have, we may prefer to use adjacency matrix or adjacency lists. If we have, if the number of edges is low, we have few edges, then in adjacency, then adjacency lists use less rooms of the memory because the number of edges is low. So the size of a storage of adjacency list is less than adjacency matrix if we have few edges. But if we have many edges, for example, if we have a complete graph, then adjacency list has many records in the linked list, and the memory size of adjacency list becomes greater than adjacency matrix. Okay, so depending on the number of edges, we may prefer to use adjacency list or adjacency matrix. This is a comparison between the size of memory of these two data structures. What about the speed? What about the time that is for accessing these data structures? If we are going to check, whether there is an edge between two vertices in adjacency matrix, we can easily check it. It's enough to check the room Aij to see if there is an edge between I and j, or there is not an edge. So we can check in a short time that there is an edge between two nodes, between two vertices in adjacency matrix. But in adjacency lists, if you are going to check that is there an edge between two vertices, we should traverse a linked list. For example, if you are going to check is there any edge between 3 and 2, we should go to the linked list of tree and traverse the linked list and find if and check if there is a record with the value of 2 or not. Okay, so checking existence of an age is slower and takes more time in adjacency lists rather than to adjacency matrix. So adjacency matrix is has more speed, and we can check existence of an age more rapidly than adjacency list. Okay, we can write this. We compare storage, your size of storage, uh, four has two neighbors, vertex 3 and vertex 5, but both neighbors has visited or already visited. So there is no neighbor for vertex 4 that has not visited. So we cannot continue. We cannot go from vertex 4 to a unvisited neighbor. So we return back because we are nothing to do. We are nothing to do in vertex 4. We comes back. Okay. So we return back from node 4 to node 5. When how we reach to node 4? We reach to node 4 from node 5. So we say parent of node 4 is 5 because for the first time I reach to node 4 from node 5. So we set the parent of node 4. We set the parent of node 4 to node 5. So when we are in node 4 and we cannot continue, we return back to its parent. Its parents by its parent we mean the node that we come from there to node 4. We come from node 5 to node 4 for the first time. So the parent of node 4 is node 5. When we return to parent. Okay, so we return to node 5. At the moment we are at node 5 and we are going to continue. For continuing, we should go from node 4 to one of its unvisited neighbors But also node 5 has no unvisited neighbor, so we should return from node 5. What's the parent of node 5? The parent of node 5 is node 3, because we have come to node 5 from node 3. Parent of node 5 is node 3. So when we return from node 5, we go to its parent. So we return to node 3. No, we are in node 3. Okay. In node 3, we try to continue the algorithm. From node 3, we try to go to an unvisited neighbor. Node 3 has 4 neighbors. 2 of them are visited. Node 4 and node 5 has visited before. So we have 2 options here. We can go to node 1, or we have go to node 6. Suppose we go to node 6 and visit it. Okay. We are at the moment at node 6, and the parent of node 6 is node 3, because we come from node 3 to node 6. Okay, we are at the moment at node 6. We are going to continue the algorithm. We go to an unvisited neighbor. Node 6 has 2 unvisited neighbors. Node 7 is unvisited. Node 2 is unvisited. We can select one of them and go to it. We select node 7 as an unvisited neighbor of node 6. The parent of node 7 is set to node 6. Okay, we are at the moment at node 7. We should continue. Node 7 does not have any unvisited neighbor, so we should return. We should return from node 7. We return to its parent. Its parent is node 6, so we return to node 6. At the moment, we are at node 6. We try to continue. Is there any unvisited neighbor for node 6? Yes, there is one unvisited neighbor, which is node 2. We go to node 2. And the parent of node 2 is set to node 6, because we come from node 6 to node 2. At the moment, we are at node 2. We try to continue the algorithm. We should go to an unvisited neighbor. So we go to node 1. Node 1 is an unvisited neighbor of node 2. Okay. Then we set the parent of node 1. The parent of node 1 is node 2. At the moment, we are at node 1. We are going to continue. We should go to an unvisited neighbor of node 1, but there is not any unvisited neighbor for node 1. So we should return back. We return back to its parent, which is node 2. We return back to node 2. Now we are at node 2. Is there any unvisited neighbor for node 2? No, there is not any unvisited node. There is not any unvisited neighbor for node 2. So we return back from node 2 and we go to its parent, which is node 6. Now we are at node 6. Is there any unvisited neighbor for node 6? No, there is not any unvisited neighbor for node 6. So we return back from node 6, we return back to its parent, which is node 3. Now we are at node 3. Is there any unvisited neighbor for node 3? No, there is not any unvisited neighbor for node 3. So we should return back, but node 3 is the starting node, and there is not any parent that we should return back to it. So here the algorithm finishes because we are at the starting node and there is no unvisited neighbor. So the algorithm finishes here. Okay. This is the DFS algorithm. Is there any question?
Doctor, please, the DFS algorithm, does it have a basic move, a basic strategy for movement from node to node? I mean, can we start from left and exploring the other nodes, or moving from right at the first?
No, it's free. It's arbitrary. You can go to any unvisited neighbor. There is no priority. When you are at a node, you can go to any of its unvisited neighbor. There is not any priority for unvisited neighbors. So you can arbitrarily you can select arbitrarily one of the unvisited nodes. Okay. One of the students asked why we select node 5. It's selected at random. When we was at node 3 at the first of the algorithm, we was at node 3. We have four options. We can go to node 1, we can go to neighbor 1, we can go to neighbor 4, or we can go to neighbor 5, we can go to neighbor 6. We selected to go to neighbor 5. It is completely random. There is no reason for it. You may select go to another unvisited neighbor. There is not any priority between unvisited neighbors. You select it in random. Okay. There is no rule. Yes, there is no rule. You from each node, you can go to any of its unvisited neighbor. There is not any priority between them. You can select any of them in random. Okay, any question?
Sorry, doctor. When it found the goal, return to the next to the same road, or stopping only? When the algorithm found the target or the goal, is it stopping or return of the same road?
There is no goal. The goal there is no goal. The goal is visiting all the vertices. We should visit all the vertices. Okay.
If they have goal.
It is not a specific vertex that we should visit it. We should visit all the vertices. Okay.
Yes, just exploration.
Not stopping, visit all the vertex.
The algorithm stops when we come back, we return back to the start node. Okay. And there is not any unvisited vertex that we should that we can go to it. So the algorithm stops. The condition for stopping the algorithm is we we be at the starting vertex and there is no unvisited vertex. There is not unvisiting neighbor for the starting vertex, so the algorithm cannot continue and stops. Okay, but please note that there is a note here. If the graph is disconnected, okay, if the graph is disconnected, for example, something like this. If the starting vertex is, for example, 2, from 2 we go, for example, to 3, visit it, then we return back to visit node 5, then we return back to the neighbor. So the algorithm stops, but we do not visit node 1 and 4. This is because the graph is disconnected and there is no pass between these two parts. Okay, so the algorithm may stops, but the graph may not, but we may not visited all the vertices. This is because this connectivity of the graph, or even we may have connected graph, but if the graph is directed, okay, this problem may occur. This problem may occur again. For example, 1, 4, 2, 3, 5. If we start from node 2, we cannot go to node 4 and 1 because there is no edge between 2 and 4 and between 2 and 1. So node 2 has only two neighbors. I mean, node 3 and node 5 are the neighbors of node 2. Okay, so from node 2 we can only go to node 3 and node 5, not to node 1 and node 4. So from node 2 we can go, for example, to node 3 and visit it. Then there is no option to continue, so we return back to node 2. Then from node 2 we go to node 5, visit it, and return back to node 2. Then in node 2 there is not any option. There is we cannot continue, and the algorithm stops because there is a known unvisited neighbor for node 2, but we have node 1 and node 4 that is not visited. This is because of direction of the edges. So if the graph is directed or the graph is disconnected, the algorithm may be finished, but we do not visit all the visited all the nodes. Disconnected graph.
So, Doctor, is that meant now we have 3 start points?
Directed graph. So what we should do, what we can do for directed graph and disconnected graph. For disconnected and directed graph, we should repeat the algorithm from another unvisited node. Okay, so if the algorithm finished, but there is until some unvisited node, we can start the algorithm from one of them. For example, we can start from node 4, then we go to node 1 and visit it and return back to node 4. So we should run multiple times. The algorithm should run algorithm for other nodes. Also here for this sample, we start again from an unvisited vertex. For example, a start 2. In this example, algorithm finishes for node 1 because there is not any option. Then we have to run for the third time and start from another unvisited node. So we should start from node 4. So in this example, we should run 3 times the algorithm to visit all the nodes. For the previous example, 2 times is enough. For a connected graph, 1 time is enough that we visit all the nodes. Okay, is it clear? Our lecture was about DFS and BFS, but I should define